Okay, so in this section we're going to be looking at sample proportions. So we're going to jump right in here with a little kind of example, just kind of a little bit of review here, looking into kind of what happens to shape and center and spread. So this example right here is essentially you're looking at a giant candy machine that has Reese's Pieces in it. Okay, and so in these Reese's Pieces parts of the machine here, you've got two things going on here. So you've got the one here on the left, you'll notice has a sample size of 25, and the one here on the right has a sample size of 50. They both have the same p-value. Okay, so this is on this particular software information there, this is my p-value right here. So they both have a p-value of 0.45. You'll notice their p-hat is a little bit different, okay, but they both have a p-value of 0.45 of that one particular sample is a little bit different. So this is a sampling distribution of p-hat. So you notice both of them, there's 400 samples. Okay, so if you counted all these little dots here, there should be 400 dots on the dot plot here. Okay, each sample on the left here, each sample was 25 candies. Okay, and on the right, each sample was 50 candies. And this was done 400 times, simple random samples here. Okay, and so this is a sampling distribution of our p-hat values for those 400 different simple random samples here. And so if we look at it, our means are very close together. Okay, regardless of the sample size, the mean is still essentially the same. Okay, but when we use a larger sample size, so when we use a larger sample size here of 50, what you'll notice is that the spread, your standard deviation, changes. It goes from 0.105 down to 0.07. So it decreases with my larger sample size. Basically what that tells me is I get less variability. And you can see this because they're on, they're not exactly on the same scale. Okay, you'll notice this one goes, on the left it goes from 0.1 to 0.8, where on the right it's going from 0.2 to 0.7, but that also would be an indicator that your variability is not quite as large. And if you look at kind of where things are clustered here, we're clustered mostly between 0.3 and 0.6. Okay, where over here I'm going much closer down to 0.2 and up higher by 0.7. So the larger, as I increase my sample size here, I'm going to I'm going to change the spread. And in this case, my spread decreased. So let's look at this one here. So in this one, I've got the same candy sampling machine. Okay, I took 400 samples, but this time my p-value is 0.15 instead of 0.45. And my sample size is different in each one. Again, on the left I have the smaller sample size of 25. On the right I have the larger sample size of 50. 400 SRSs, so I've got my dot plot on each one of my sampling distributions here. Okay, so if I look and I compare both of these to one another, okay, again, I've still got my mean is pretty close, 0.143, 0.148, but when my sample size goes up, my standard deviation over here goes down. My variability or my spread goes down to 0.051 as opposed to 0.069. Okay, one of the things I do want to point out, and it was kind of pointed out in the last one, is you need to be careful about just looking at the graph. And if you just looked at the graph of these two, you might not necessarily notice some of these things. So make sure you're looking at all of your data and taking in all of your information. Okay, so let's kind of take a look now about kind of summarize some of our sampling distribution information of our p-hat. Remember, our p-hat is our sample proportions. Okay, so the p-hat would come from each of our samples, whereas p would represent the entire population, where the p-hat is from each statistic. Okay, so let's talk about shape here. If I'm looking at the sample distributions of p-hats, okay, so my shape in some cases is approximately normal, okay, and so it's almost normal in some cases, which will be helpful because we're pretty confident, hopefully, with our normal problems by now. That will depend upon sample size, as well as your p-value for your entire population. Okay, as for our center, okay, our center is going to be the mean of the distribution. So the mean of the sampling distribution. And so the mean of all of our p-hat samples should be equal to p. Okay, remember our sample proportions? They are an unbiased, I can't spell. Our sample proportions, I ran out of room. Okay, but our sample proportions, they are an unbiased estimator. Okay, so they should be, when I take the mean of all those different sample proportions, if we're talking about those candies, basically our p-hat was how many of them were orange, I believe. Yes, how many of them were orange in each sample. Okay, so if I take the average of my, hundreds and hundreds and hundreds of samples, that should be the same as my proportion of all the candies that are orange in the entire population. Okay, as for our spread, okay, so the spread for a specific value of p, okay, is my standard deviation. Okay, so when we're talking about spread here, we're referring to our standard deviation, and that's going to get smaller as n gets larger. So my standard deviation of the population is going to be dependent upon n and p. And so as n increases, my standard deviation should go down. So if our population size is really, really large, so with our example here, if I had lots and lots of candy in the machine, thousands and thousands of candies in the machine, okay, and I've got X, which equals my successes. So if my population size is really large, and I've got X, which is my success, X, which is equal to my successes, can have a binomial distribution. If you remember from the last chapter, we talked about binomial versus geometric distributions, right? And our binomial distributions were how many successes we had, okay? Essentially our probability of success, where our geometric distributions were how many attempts did it take to get a success. So if our population size is really, really large, then our X values, our successes here, can have a binomial distribution. Okay, and so if our sample proportion of successes is going to be closely related to our X. Okay, and so our X is going to be, again, if that's a success or not. So then our p hat can be equal to, we count our number of successes in the sample, so that would be X, right, over the size of the sample, because this is a binomial distribution. So basically all this is saying is what you assumed we did to begin with. If I had a sample size of 25 candies, then I would just count that 4 of them were orange, and 4 over 25 is going to be my p hat. Okay, so let's do a little bit of binomial random variable review. Okay, so let's say our binomial random variable here is x. Okay, so I've got my binomial random variable of x. If you'll remember back from chapter 6, right, our mean of x is equal to n times p, so n times the proportion. Okay, our standard deviation is equal to the square root of the variance, right, np times 1 minus p. Okay, and so if I'm going to apply this out towards p hat, right, so what this is going to look like here is if p hat, okay, so if p hat is equal to x over n, that's the same as saying it's equal to x times 1 over n, right? So basically what I'm doing here is I'm multiplying my x right? I'm multiplying by a constant. And if we think back to when we transformed data before, if I multiply by a constant, that's going to affect mean and it will affect spread. So basically what that does is that it helps confirm that p hat's an unbiased estimator of p. So for example, if I've got my mean of p hat, then that's equal to 1n times np, which would be equal to, right, these would cancel, so that would be equal to p. So that confirms there that p hat's an unbiased estimator of p. As for standard deviation, right, if I take the, let me erase some stuff. If I take the standard deviation of p hat, so standard deviation of p hat, multiply it by my constant, okay, and square root of np times 1 minus p. Okay, when I simplify that down, I get the square root of p times 1 minus p over n, which is going to see, you notice n now is in the bottom, the denominator here of this fraction. So what's going to happen is it's just proving that as I increase n, or I increase my sample size, I'm going to decrease that standard deviation. Okay, so, but remember, multiplying by a constant does not affect the shape. Okay, so it will not affect the shape. So if these values here, so if np, if n times p, okay, and n times 1 minus p, okay, so if n times p and n times 1 minus p are at least 10, okay, you need these to be greater than or equal to 10. So add those two together, and they are greater than 10, you can use a normal distribution, okay, which will help you when you're trying to calculate information. So you can use a normal distribution to approximate your sampling distribution of p hat. Okay, so if n times p plus n times 1 minus p is greater than or equal to 10, you can use a normal distribution for approximating your sampling distribution of p hat. So I'm going to kind of repeat myself again here, but I just want to make sure that we're clear here. So when I'm looking at when I'm looking for the sampling distribution of a sample proportion, so basically of p hat. Okay, so my simple random samples of size n from a population of size capital N with a proportion of p and successes, right? Okay, so basically that's what my sampling distribution would be. It's going to show my SRSs of a sample size of n that came from a population of size capital N, and they have a particular proportion, P, which is going to be of my successes, and whatever those successes may be. Okay, where P hat is going to be my sample proportion. Okay, so when I have my mean of my sampling distribution of p hat, the mean of the sampling distribution of p hat is equal to p. Okay, the standard deviation of p hat, of the sampling distribution of p hat, okay, is equal to the square root of p times 1 minus p over n. Okay, and if my 10% condition is satisfied, remember this from before, right, that my sample size had to be less than or equal to 1/10 of my population. So if my 10% conditions are satisfied, okay, then I can say that I can use this information. Okay, I can use these numbers, basically, this setup, if my 10% condition is met. So keeping my sample size at less than or equal to 10% of my population. Okay? As n increases, so as my sample size increases, the sampling distribution of p hat becomes approximately normal. Okay? So it'll become approximately normal, and I need to check for what's called the large counts condition. I can say that it's becoming approximately normal if it meets the large counts condition. And the large counts condition is that NP is greater than or equal to 10, and, not either or, and N times 1 minus P, that's the multiplication, is greater than or equal to 10. So if both of those conditions are met there, that's my large counts condition, then I can say that this is becoming approximately a normal distribution. Okay, let's run through an example of this. Okay, let's go through the example. I think all of this stuff makes way more sense when we're going through examples of it. It's too abstract, I think, without it. Okay, so looking at this example here, I've got about 75% of young adult internet users ages 18 to 29. They watch online videos. Suppose that a sample survey contacts an SRS of 1,000 young adult internet users and calculates the proportion p hat in this sample who watch online videos. So number one, what's the mean of the sampling distribution of p hat? And explain how you know that. Okay, well, my mean, so for number one here, my mean of p hat is equal to p. So that is going to be equal to 0.75. And I know that basically writing this formula right here tells why I know that. Okay, so for number two here, find the standard deviation of a sampling distribution of p hat. Check that the 10% condition is met. Okay, so my 10% condition would be that my 1,000 young people, okay, if I multiply, let's do this first. Okay, if I take these 1,000 young people and I multiply that by 10, that means my population has to be 10,000, right? Because 1,000 would be a tenth of 10,000, or 10% of 10,000. So that means my N would have to be 10,000, my whole population. Okay, and so I would say the 10% conditions are definitely met because there are more than 10,000 internet users between the ages of 18 and 29. Okay, and so your population is significantly bigger than just 10,000. So that part is met. Okay, so for my standard deviation of p hat is equal to p times 1 minus p over n. So when I plug that stuff in, I get my square root of 0.75 times 1 minus 0.75 over 1,000, which gives me 0.0137. So for number three, it asks if the sampling distribution of p hat is approximately normal, and check that large count conditions are met. Okay, so let's go ahead and check those. So to check that large count conditions are met, I need to make sure that n times p is greater than or equal to 10, right? So n times p would be my sample size, which is 1,000, times my proportion, which is 0.75, which is 750, greater than 10. Okay, I also need to make sure that n times 1 minus p is greater than or equal to 10. Okay, so again, 1,000 times 1 minus 0.75, okay, which gives me 250, so again, greater than 10. So my large counts conditions are met, so I would say that yes, this is approximately a normal distribution. And then number four, ask if my sample size was 9,000 rather than 1,000, how would this change the sampling distribution of p hat? Okay, well, my mean should stay approximately the same, right? So my mean, because this is here. So my formula for my mean should be the same, right? Still going to be 0.75, okay, because it's equal to p. And my standard deviation, when I calculate standard deviation, I still have 0.75 times 1 minus 0.75 over, though, now 9,000, and then take the square root of that. Okay, and so that is going to give me 0.0046. So my mean stays the same, but my standard deviation or my variability would go down for that sampling distribution. Okay, so let's do one more example, this time with a normal calculation involving p-hat. So I've got here a polling organization asks an SRS of 1,500 first-year college students how far away their home is. Suppose that 35% of all first-year students attend college within 50 miles of home. Your problem is find the probability that the random sample of 1,500 students will give a result within 2 percentage points of this true value. Show my work. So this is a normal problem. So remember, when we're doing a normal problem, step 1 is kind of to state all of our information. State the distribution, the values of interest. So basically what we're looking for is the probability that p-hat falls between 0.33 and 0.37, because I want to see if that sample will be within 2 percentage points of the true value, and the true value is 0.35. So if I'm writing this in symbol-wise, basically I'm looking for the probability that 0.33 is less than or equal to p-hat. So of my particular my proportion of my particular sample, that I want my proportion of my particular sample to be somewhere in between 0.33 and 0.37. Okay, other information that I know here is I've got an SRS of size n equals 1,500. And I know that the proportion for this is 0.35, and that is students. Remember, they love context, right? So students attending college within 50 miles. Okay, so that's my 0.35. Okay, I know what I know about the sampling distribution for this is I know that the mean of the sampling distribution is going to be 0.35, because it's going to be equal to my proportion, because it's equal to p. Okay, I can always add that in there, add that it's equal to p there. Okay, as for the standard deviation, I need to check my 10%. Okay, right? So basically I know that I've got 10 times 1,500, which would give me 15,000 for my population as a whole. Okay, and I would say that this would definitely qualify as a sample that is less than 10% out of all first-year college students in the, I'm going to assume this is in the U.S., but in the country, or, you know, I don't know, it could be around the world, but there are still going to be more than 15,000 of them. Okay, so you've definitely met your 10% conditions there. Okay, if I'm looking at my standard deviation of p-hat, right, remember that is p times 1 minus p divided by n. Okay, so when I plug in those numbers here, I get 0.35 times 0.65, 1 minus 0.35, right, divided by 1,500. And then I take the square root of that, so I get 0.0123 is my standard deviation for this. So can I use normal distributions to approximate this? Well, remember, I need to use my large counts here to determine if I can use normal distributions here. So n times p is going to be equal 0.35 times 1,500. Is that greater than 10? Okay, yes, it is 525. So that's greater than 10. And then I also have to check my n times 1 minus p. So 1,500 times 0.65, which is also going to be greater than 10. It's going to be 375. So you've met your large count rules, so I can assume your normal approximation here. So then I would need to draw that out, right? So if I'm going to draw that out, where's the undo button? Okay. Okay, remember the problem, because I'm going to get rid of the problem because it's taking it away from me. Wait, here we go. There we go. Okay, so if I'm going to draw this out here, right, I'm going to draw my curve, draw my normal curve, right? I'm going to put my mean in the middle, right, at 0.35. Okay, I'm going to label my curve, right, a normal distribution of a mean of 0.35. Whoops, I closed it too soon. With a standard deviation of 0.0123. 0.0123. So I label my curve. Okay, I'm looking for 0.37 to 0.33. Whoa. To 0.33. So I'm looking for this area right here. Okay, and so I'd pretty much have my stuff labeled and taken care of here. Okay, and so now I need to actually perform my calculations. Again, you could do this using technology, or you could do this using z-scores, right? I could find my z-score of 0.33, and I could find my z-score of 0.37, right? Take my value minus the mean and divide it by the standard deviation to find my z-scores. Okay, and then I could use my tables to determine what that area is there, or I could use my calculator. And if I'm using my calculator, right, I'm listing everything out, right? Normal, CDF. What is going on? I'm struggling to write, guys, sorry. So normal, CDF, and then I'm going to put all my information in, right? My lower, and I'm going to identify it. Okay, parentheses, and then I'm out of room. Lower is 0.33, right? Upper is 0.37. My mean is 0.35. My standard deviation is 0.0123. Close my parentheses, and that's going to give me an area of 0.8961. And if you use z-scores, you get 0.8968. And then you have to do step 3, which is to actually answer the question. Don't forget to do that, right? So if I'm actually answering the question, I've got about 90%, right? 0.8961. So about 90% of your SRSs with a size of 1,500 will give me a result within 2 percentage points of the true percentage points of the truth about the population. Okay, so about 90% of your SRSs are going to give you a value within 2 percentage points of the truth of the population.